I'm muted right now. Having some lunch. Made a milkshake right here. Got my milkshake. So might try to see like I can disappear and I can have my milkshake. There we go. Perfect. Someone's watching right now and they're like, where'd Brian go? He went away. We are back though. Just trying to eat healthy. Some bananas, some strawberries there, and some, was it oat and almond milk? Some healthy stuff. Good healthy foods in a milkshake. No milk, no ice cream. It's a bummer. It's a bummer. I hope everyone's doing well. Got the stream going here. Let's take a look at what we have for this week. I'm going to go open up 201 and let's start talking about this week and what's going on. Chapter 5 is a big chapter this week. Let's go take a look at those assignments right here. Okay, so we got it up. And let's go take a look at the main screen right here. Let's do it. Now, if you are here in the chat, feel free to say hey and ask questions at any time. So you'll see right here, we have Canvas Content Quiz 2. So we only got the second one? Yeah. We did the first one last week. I think we also looked at the second one last week. We had a little bit of a free time. The standard deviation, that is chapter 5. That's coming right up here. And then we get into some big assignments due this week. These are major assignments, both due on Wednesday. So we'll probably take a look. I think people are asking about Chapter 5, Part 2. If you're here in the chat, let me know. But Chapter 5, Part 2 is going to be a very tough one. And then we see right here Canvas Content Quiz 3, which I don't think we've done a version of that yet. So maybe we'll do that next. We have here Chapter 6, and then we have some lectures. And then next week, and we're getting close to the test. Next week, test on Wednesday. So that's not going to be this week. That'll be in next week's kind of talk about what we have going on. I'll send out announcements. We'll do a review, all that great stuff. So you see right here, the exam is coming up. All of this good stuff right here. So with this, let's go take a look. And I think I have a person who's taking it early, hence why you see it twice on my screen. I believe everyone else is taking it right here on Thursday. Let's just double check the dates right here. Put if the class is over. And everybody is taking it on the 24th. We have to work in individual plans sometimes, so mine shows more dates. Yours is on Thursday. I didn't want to scare everybody, but yours is on Thursday, unless there was a person who I think reasons just had to work out things. So yes. So please contact me if there are things, but mine shows everything. I get to see everything on here. Good stuff. We got the test your system just to make sure everything's working, and that is due on Sunday. It's just a test, nothing worth a grade. Let's go take a look at Canvas Content 3, which I don't think we've done, and let's throw in a cut in the video. If you're here, though, ask questions. Ooh, it's Chapter 5. Good stuff right here. Take one last bite of the milkshake right here. Okay. Milkshake. Almost done. Good to go. Canvas Content number 3. Let's do this. So this is over one of the more difficult chapters. Chapter 5 right here, covering the normal curve. Let's go ahead and do a preview version of it and solve the questions and get some practice. So, Chapter 5 is over the normal curve. Let's talk a little bit about these concepts and ideas. Funny enough, we were just talking about this in 320. We're talking about the normal curve and normally distributed data. So let's talk about normally distributed data and what it means. So when we talk about the normal curve, we're talking about the bell-shaped curve. So you've probably heard this before. Bell-shaped curve, the Gaussian distribution looks like this right here. And what do we mean when we say it's normal? Well, the idea of being normal, capital N right there, is going to be that it is unimodal, meaning one mode, and it's also symmetric. So the idea of being normal is unimodal, one peak right here, and also symmetric. And that's what we're talking about with the normal. Now, we have two numbers that we use when we describe a normal curve. The first number right here, I want those things to go away. Look at this. Magic. There we go. The first number being right here is going to be the mean, and the second number is going to be the standard deviation. So the mean is going to go at the center of the curve. We have here a mean, and then we go up and down 3 standard deviations. It goes out further than this, but you generally don't see data outside of 3 standard deviations. William, good to see you here. The normal curve was made by Alexander Graham Bell. No, it was made by Gauss. It's called the Gaussian curve sometimes. I'm trying to think of Gauss's... Look up Gauss's first name for me real quick. But Gauss is a Swedish guy, I believe. So the normal curve was made by Gauss, called the Gaussian curve sometimes. William right there messing with us. 20 points. Let's throw some William some points right here. Is Mubot you awake? Yeah, Mutebot's awake. Let's throw some points. So the normal curve made by is it like I can't think of Gauss's first name. But we go up 1 standard deviation and down standard deviation. So we go plus 1 standard deviation, plus 2 standard deviations, plus 3 standard deviations, down 1 standard deviation, down 2 standard deviations. And we'll see an example with this here in a moment. Down 3 standard deviations. And this is where we would expect the middle 68% of data to be within plus or minus 1 standard deviation. And we were just doing confidence intervals a second ago in 320. 95 is basically plus or minus 2. And then 99.7 is going to be plus or minus 3. So a real quick contextual thing on this when you think about it. If I told you your test scores were normally distributed with a mean, normal curves first formulated by... Really? I'll have to look into that. Well, then Gauss popularize it? How would you feel, William, if I told you the exam scores were normally distributed with a 94 and a standard deviation of 2? How would you feel about this? If I said the exam scores for 320 were normally distributed, I've got my lunch right here. I'm going to drink the rest of my milkshake lunch in the background. So, how would you feel about that? What do you think? I'd love that. What would that tell us? What would that tell us? Well, we'd know the mean is 94, and we'd go up, and we're just, look what we're doing. We're just going up 2 every time. Oh, wow. So we would expect the higher grades to be like 98 to 100, and this is like the percent of area under the curve right here, saying that we expect very few grades to be in this range, but still there would be some at that high range right there, a very small percentage. And going down right here, you can see the lower grades are not that bad. The lower grades, you would expect maybe the lowest 2.5% of grades. If you go down here, the lowest 2.5% of the class, and I just got this by taking the outside area of 95, the lowest 2.5% of the class would make a 90 or below, which is 2 standard deviations below the mean. So this would be very good. You might say, well, I mean, very, very small percentage of the class is making below a 90, which is, that's where an A is at. So this would be a very small variation. The standard deviation shows us the variation between each of these. So this 2 right here represents the spread of the data. Remember, standard deviations to measure a spread. So each of these is spread out by 2, and the mean is the center of the distribution. Really good review from earlier topics. If you remember shape, center, spread, the shape is normal, the center is the mean, and the spread is the standard deviation. So you literally have shape, center, spread all right here. And when we have normal data, we'll use the mean and the standard deviation. So kind of a really, really great review right here. Oh, sorry about that. I tried to mute the cough. I'm not dying, I swear. So it says the finishing times of a local 5K, 3.1, something like 1.2 miles, I think. Road race follow a normal distribution with a mean of 25 and a standard deviation of 3. What percent of runners do you expect to finish above 31 minutes? Can anyone find me a Z-score for this? William, really good practice. What is the Z-score for 31 minutes? So if you notice, it says the mean here is 25 and the standard deviation is 3. So let's put in the info here. We'll leave those. Maybe those will come in some use. We'll bring them back. The mean is 25. The standard deviation is 3. And so let's put in our data. So we're just going to put the context here. I call this the context version. We've just got the standard version up top. And we're just going to put 25 and 28. And what? 21? I mean, 31 right there. 34. And so then we have to ask ourselves, what is a Z-score? Which say, well, what the heck is a Z-score? And a Z-score is how many standard deviations something is above or below the mean. So we actually have the answer on the screen right here. The answer on the screen for a Z-score is found by observation minus mean over standard deviation. So standard deviation is going to be sigma in this case, and that's a Z-score. So we observed somebody having a time. The mean is really 25 minutes, 25 minutes. Did Terry write this one? We observed someone running it in 31. That's the observed time. And then we expect someone on average to run it in 25 minutes. And then the standard deviation is 3. And if you can see right here, that means the observed value was 2 standard deviations above the mean, which we can see right here in this distance. This distance tells us it is the observed observation of 31 minutes was 2 standard deviations above the mean. So that's what the z-score is telling us, that 31, an observation of 31. You could do a more difficult one, like I could say 32, and you could see here we could take 32, which is not the question. But 32 minus the mean, well, whoops, 32 minus, yeah, it's not minus. 32 minus the mean is 7, which is how far it is away. And then we divide by the standard deviation, which is 3. And then we'd get here 2.33, which means it's 2.33 standard deviations above the mean. So this one is 2 standard deviations above the mean, which is the z-score for the problem we should be doing. And that's the answer right there. In 1992, an article, the Journal of American Associations for whatever, medical associations, researcher reported that a more accurate body temperature was 98.2. It's interesting because mine's always way lower than 98.6, with a standard deviation of 0.7. Assume that a normal distribution is appropriate, and the middle 60% of temperatures range with the z-scores of the following. Now, this is showing the z-scores right here. So you can see here -1, 1. It's the exact same thing we've been drawing out here this whole time. We just need to put our numbers on here. So all we're doing is just substituting in our numbers. And we can get a good guesstimate of this answer by looking at what we put in here. So once again, we're just going to plug in 98.2. We could also use the David M. Lane applet here in a second. 98.9, and we could plug in here 97.5. I'm not going to continue out further because we're looking at something around here-ish. And I think that said it's the middle 60%. So let's show it the way they're showing it. Oh no, come on. I was so close. There we go. Boop, boop. And then this is showing the middle 60%. And it's giving us the z-score for this. So we got here the middle 60. And yours in the what we see right now on the graphic is showing us. Oops. Really? There we go. There. We'll put that back in here. There we go. It's showing you these numbers here, but I was able to add in the context of these numbers here. This is using the context above to see kind of where one standard deviation would be at above and below. And we are doing the middle 60%. Looks like I'm saying middle 6, but this is middle 60%. So with this being the middle 60% right here, well, then what does the question ask us? Now that we have a little more context on here. What is the 80th percentile of body temperatures? Now, you might say, well, we don't have the 80th percentile on here, but we do. The 80th percentile, percentiles go from high to low. You would know up here that there's 20% up here, because just outside of the middle 60 is 40%. You've got 60 inside, so that leaves 40 outside. And so you might say, well, where's the 80th percentile? The 80th percentile is going to be right here, because below here is 80% of the curve. So that's the 80th percentile, because below there is 80% of the curve. Now, an important thing to know is that this is telling us the z-score for this, I think, was 0.842. If it is that, that means I've memorized it, and that's kind of sad. Yep, that's sad. Not really sad. But that is the z-score for this observation. Now, what is that telling us? Remember just a moment ago we did a z-score? A z-score, Robbie, good to see you here. Robbie, ask any questions you have. Let us know. A z-score tells us how many standard deviations something is above or below the mean. So this line right here is 8.42 standard deviations above the mean. Just think about that. You're saying we need to go up 8.42 standard deviations above the mean. So we need to take the mean and add to it the z-score, which tells us how many standard deviations, and times that by the standard deviations. So we go right here, and we're just saying, well, we're at 98.2, and then we're going to add to it the z-score, which is how many standard deviations we've gone up, and then we're going to times it by the standard deviations, because that's how many standard deviations we've gone up. And that should give us the answer. So we get 0.842, and that's how far we've gone up. And what's really great about doing it this way is you'll notice this 98.78 is right here, like it's below this. Like we could tell, okay, look, 98.2, 98.9, And our answer right here is in between. I'm going to try and make it so you can see it. But this answer right here has to be kind of closer to this. But we've got it to where the answer kind of makes sense. And we've done it. How many decimals? Round to 1 decimal point. That should do it. There's 1 decimal. The Chocolate Boom Candy Company manufactures many types of different candies. Their most popular Valentine's Day candy box follows a normal distribution. So we got another normal distribution right here with a mean of 469, a standard deviation of 15.3 grams. You decide to buy a box of candy. Your candy box weighs 499. Calculate the z-score. So we can do this one a little bit quicker because we've done this stuff a few times now. Z-score is just going to be observation minus mean over standard deviation. Let's mark our notation so we know how to do observation minus mean over standard deviation. So this is going to be what we observe, which is the y value right here. That's just what we observe in our data set. The mean is what we expect, which is going to be mu. And this is going to be sigma right here. So we need to do observation minus mean over standard deviation, which is just going to give us the distance something is away. That's the top part of the equation. I think it broke. Really? Yeah, it's broken. We'll just ignore it. It's probably going to say sniffing tool crashed. So the top part of the equation is the distance two things are away. You got me? And so the distance these two things are away is calculated by just taking the two values and subtracting them. We observe our box having 499 grams. We expect our box to have 469, which is a distance of 30. That's how far they are away. Then we're going to divide this by the standard deviation to turn it into a standardized metric, a z-score. We're just going to get like 2.94, 2.96. Oh, I see what they did there. That's classic. 1.96, excuse me, 1.96. I don't know why I said 2. I was thinking it was close to 2 and then my brain broke. So we've got here the distance of 30 calculated by these two values, how far they are away. That is totally, is it working? Nope, not working. Let's reset sniffing tool. I do not want to save that. Sniffing tool, you doing okay, man? Doing good? You want to change to the highlighter? Oh, you don't? Okay, we'll reset the computer later. We'll see if you're okay then. So we see here the z-score has been calculated. We'll hope everything's good. And we'll go back here to 2 decimals. There we go. There's the 2 decimal calculation of the z-score telling us how many standard deviations an observation is above or below the mean. An article found temperatures to be equal to this and this. And then we have the area shaded right here. What percent of adults have a temperature higher than this right here? Now, if you notice, we say that this is 13%. So this one, and these are great test questions. A lot of people ask me, Brian, how do I know what to do on the test? And these questions are basically test questions. When I say basically, some of them are test questions. So when you look at this, you immediately want to start graphing this. And you want to say, okay, I know it's telling me that the outside shaded area, both of these put together is 13%. Well, that means in the center right here is 87% because it has to be 100%. Just think of it as a total of the curve. But then also that if you cut this in half due to the law of symmetry right here, and you could confirm for yourself that this is symmetric, but it is a symmetric thing. We could z-score it. Why not? Just to confirm that these are symmetrically away. Well, you don't need to z-score them. You could just do the distance. And the distance that this one is above is this. It's this far above. Is 1.06 above, and then the distance the other one is below is going to be the same distance, 1.06, and so it's that far below. They are both symmetric distance away, which confirms that these will be symmetric or the same size because you're as far above as you are below. Now, if you look at the question asks specifically above this point right here, what percent of observations would we expect? Higher than this value right here of 99.26, which we see right here. So the answer is 6.5%. Let's make sure we do it as a proper percentage or whatever it would like. So it wants it as what percent of adults. So if we're doing percent, it's going to want percent. Let's hope it doesn't get mad. I think I've changed these all around, so it will accept it. Yeah, so it says percent. So let's enter it in as a percent, not a decimal. How does the normal probability plot determine if a distribution is normal? William, if you are still here, this is probably one of the best questions 320-201 crossover we could possibly ask for. So when we talk about a normal probability plot, we are actually doing this in R all the time. There's a little bit of a 320-201 crossover right here. And you'll be seeing this tomorrow especially. A normal probability plot is right over here. And this one does indicate normality to me. A normal probability plot, which is at the end of chapter 5, helps us determine if values follow the normal or they don't follow the normal. The red line down here, the center, which the red line will follow the normal, is going to show us if things are normal. We can get non-normal, so let's go random exponential. A non-normal normal probability plot will look something like this. So what is it not like? Oh, I put in... Here's a very non-normal. Let's clear out the plots and make it so it's nice and big. This is a ridiculously not normal one. So if you notice, it does not follow the linear pattern of the normal. And then a very normal one will follow it. And it might not look perfect. I'm just generating ones right here. These are all normal right here, as in they all follow the line basically very well. And then this one right here does not follow it at all. These are all just random plots that either follow the normal or don't follow. This one does not follow. So something that does follow the normal right here would be something like this right here, which follows the linear pattern shown by the normal quantile plot, also known as a normal probability plot. So when the line is straight, that's going to follow it right there. Let's hope we got everything correct right here. Did we enter everything in the right way? What did we... Wait. With a mean of this... Oh my gosh, I just z-scored it. No! What percent of runners? 2.5 is the answer. 2.5 is the answer. Ooh, Brian missed a question right here. So what percent of runners would we expect? If you go back in time, I actually showed that answer over here. We can go way back in time. I don't know if we can go far enough back. Sometimes the time stops. But here we are with this. And we had it showing on the screen just a little while ago. I z-scored it, but I didn't. We had it on here previously. There is the 2.5. So the answer would be 2.5. And is it longer than that? Because if it's longer and this has a different context to it, sorry about that. Uh-oh. Make sure you read it. What percent of runners do you expect to be above 31 minutes? 31 minutes is going to be a z-score of 2. And we'll show that in context right here. I just z-scored it. So we have here 25. We have here 3. We have 25. 28, 31, and that is a z-score of 2, which we found. And then we've already drawn in here from the previous one. I knew I was, like, my brain jumped a second there. I was like, wait a minute, there's one more step. So we want the percent of runners we would expect. I thought for a moment it was asking the z-score. It does have a z-score of 2, but the probability of runners taking longer than this time is 2.5 according to the normal curve. I tell you what, if you were doing this and you entered in 2, and you got it wrong, email me and I'll give you those points back. I would hate for... There, I finished my shake right there. I'd hate for someone to be like, Brian, I did exactly what you said for that question. I hit submit and I saw you got it wrong. And I was like, no, I was following your steps because you didn't read the full question, Brian. As our first error on Stats 201 for the summer. We got to stop those errors, everybody. Can't let those errors build up. Puppet Shark, no more errors, right? You're always so agreeable, man. You're always here for us, Puppet Shark. Making sure we get those right answers. Let's hop back to space. Okay, so that was the Canvas content quiz. Maybe let's take a look at some chapter 5 right here. Hop over to some My Pearson. And let's take a look. No, we can't get anything wrong. Never. I've been teaching the class 11 years. And that is the first question ever. I'm just kidding. I have been teaching 201 for 11 years, I think. Wow. 11 years. We'll see if I can get everything right after another 11 years. Let's go another 11 years. And be like, Brian, does Brian get every question? I don't know. You're always going to make mistakes. There's always going to be small errors. And that's okay. I'm just telling myself that. It's okay. It's okay to make errors. It's okay to make mistakes. That's how we practice. And then we're like, I gotta read that full question. Gotta slow down for a second here. Let's take a look at the class. Here we go. Hopping into the class. Let's go over here to course tools, assignment manager. Take a look. Good job, everybody. If you're here, feel free to ask questions. To keep doing the work. Seeing where people are at. Good stuff. Let's go here, make sure everyone's doing the work. The biggest thing is to keep doing the work. Keep doing the work. Keep on swimming. Keep on swimming. Some people are asking about Chapter 5 via email, but always feel free to swing by and I can do a direct question. So let's take a look right here. And Chapter 5, Part 2, currently on the screen. Let's go take a look. Oh, I'll do my favorite one. Why not? It's probably my favorite question. It's a lot of fun to do, just to see if you have down the normal curve. We're going to put the David M. Lane applet in the chat. David M. Lane applet's going to be super important right here to make sure we're doing all of our work properly. David M. Lane is going to give us exact calculations compared to what we were doing with the empirical rule before. So if you're watching me do the quiz before, I was using the empirical rule with the 68, 95, 99.7, but the David M. Lane applet, which you currently see in the chat, gives you exact calculations. So if you were to put in between, with z-scores right here, -2 and +2, you'll get close to 95. You get 95.449. There we go, 95.449 rounded right here, of course. But this is the exact calculation of what you'd see between -2 and +2, not 95. You basically get 68 at 68.23, I think. Am I correct? 68.26 something. I think there's another decimal to that. But you can see there's more decimals. 99.73 is this one, and there's 99.73. So we usually say 68. There's 68 in 2 seconds here. Oh my gosh. 68, 95, 99.7, and that's the area under the curve based on the empirical rule. This is the exact calculation integrating the curve for you, not a rounded version that we can memorize and keep in our head at all times. So I used a lot of these numbers myself to solve answers. The way we solve this, in the applets in the chat, is you can find out the answer to the area greater than 1.4, which is going to be this right here. 1.4 is on the right side of the curve. Now this answer, I'm just going to give a guesstimate and then show you how I'm getting it. This answer is going to be a little bit less than 10%, but a little bit more than 5%. It's going to be, I'm going to just guess about 7%. I'll explain how I'm getting that here. So we're going above 1.4. It's 8%. I should have guessed 8. I'd have been so close. Might even gotten it correct with the plus or minus it gives you on it. The reason I know this is because above 1 is 16%, basically, and above 2 is 2.5%. I also know some other numbers like 1.2816, and I know other numbers like 6.45. You notice that's 5%. So when I see this right here, 1.4, I know it's between these. So I'm using numbers I know on the curve, but the David M. Lane is going to get you the exact answer right here. So this is going to be 8.08, 2 decimals right there. Now we want the area less than, and this is kind of interesting. I think we're almost in the same spot on the curve. I just want you to think about where we're at. We're almost in the same spot on the curve, but now we're going less than. William, awesome to see you. Yep, associate y tilde x comma data equals. Perfect answer, William. Great job. And look at this, William. I just want you to guesstimate. If this is 8% above here, what do you think is about below here? As in just a close guesstimate. So if this is 8% above here, and then we're almost in the same spot. I'll see if William, you don't have to guess what William don't want. But think this is 8% above here. We just found the answer to that. So what would be a close guesstimate of the area below here? It's almost in the same spot. It's a little further over. So if this is 8% above, and we're almost in the same spot, this is probably close to what percent? So you can use this previous answer to be like, oh, this is 8% above here. So if we were to go almost below here, instead of it being 8%, we're just going to do what's called the complement, and we'll guess 92, but it's a little further over if you notice. It's a little bit further over, so I'm going to guess a little bit more because it is a little more over. So 1.45, below 1.45. Let's go look at the answer. And below 1.45, and it's 92.65, 92.65. So we were very close in our guess right here. Oh my gosh, 92.65. It can't be that large. So 92.65, and we're obtaining it by going, and here's one thing you should notice, is that your answers on this screen right here, should look like your answers on this screen right here. You notice how that graphic right here, if you take a look at it, looks a lot like the graphic right here. Like, here, I'll put them side by side so you can see if I could do it. So on that page, it's not on that page. 2 seconds. So there's that graphic. Look at me. Now look at you. Look at me. Now look at you. Look at me. Now look at you. There you go right there. Oh, you can see like, whee! There you go. Perfect. We know what's going on. That looks correct. As long as we're entering in decimals, we should be good. And now it says the area between, and this one's super tough, but it's just going to be the between areas. Like to estimate by understanding the curve, that's a little bit more than 25%. That's about 45%. So this is about 70. It's in the 70s, I'd say. I'd say 71%. That is a super hard one to guesstimate just by the shape of it. Negative 0.7 to 1.8. My guesstimate could be very far off. We're going to go to the between, and it was this, I think. And then it was 1.8, right? Ooh, was I really close? 72.21. And let me make sure I entered in the numbers correctly. 0.7 and 1.8. 0.7 and 1.8. And then you should see your graphic. So let's put this over here again. Let's click on our graphic. And then let's see, does that look like it? And I'd say yes, that does look like it. Make sure you've graphed it all in the same spot. Negative 0.7 to 1.8. Negative 0.7 to 1.8. And you see those values are placed right there. And then make sure your answer is the right answer right there. So we see it right there. We can't put it on the same screen as it. So that is looking good right there. We've done it with that answer. Good stuff. People sending me random links. And so now we go down to here. Choose the graphic. Oh, you see, this is almost a 96% or 95% confidence roll. And it wants the area outside of it. So it says greater than absolute value, greater than the absolute value of z of 1.9, which means like 2 would be greater than absolute value of 1. Or absolute value of 2 is greater than 1.9, and negative 2 would be greater in absolute value than 1.9. So this one is the correct one. It's going to be a little bit more than 5%. Probably, where's my answer thing? Probably about like 6.4%. Sure. And that's just a guesstimate because I know the 95% confidence interval, but once again, we can go right here to the applet, and let's go bring the applet on the screen. Once again, we're going to make sure our picture matches. We're going to go outside of negative 1.9 and 1.9, and it's 5.74, so I was kind of close. And let's hope we entered in everything the right way. 100%, great stuff. I was really worried I'd get one wrong there. This is my favorite, one of my favorite questions. I was like, I'm going to get one wrong. I'm going to type in a decimal wrong. I'm going to forget to do 2 decimals. Just so easy to make errors right there. What are they sending me? What is this? I'm afraid of random links. I will not click random link. You send me random link, I will not click it. That's how they get you. Your friend sends it to you, and you trust it, and then it gets you on your phone. This is bad right there. Don't do it. Don't click the random links. Unless the links are from Mubot. Mubot's a mod here. Mubot knows what's up. Let's take a look. Time for some more. Let's take a look right here. We can do the football question. It's on the homework also. Let's take a look at the football question here. In one season of a football league, the number of yards gained by each of the 156 wide receivers was recorded. A histogram of the data is shown to the right. Ooh, that histogram looks very right skewed. Right to the high, left to the low. Whatever way that little monster man's tail goes. So let's look right here. Right to the high, left to the low. Whatever way the tail goes. So got the monster man, and there's his tail right here. And that is definitely a right skewed distribution. So according to the normal model, what percent of receivers would you expect to gain fewer than 2 standard deviations below the mean? So this actually goes back to our previous questions over here. And we don't even need to insert our numbers. We can just see here at 2 standard deviations below, we would expect 2.5 according to the empirical rule, the 68, 95, 99.7 rule. And you can see it doesn't have that shape. So we're going to turn the ringer off right here. Ringer off. And so 2.5. So what does this mean? If you were to go 2 standard deviations below the mean, well, the mean is 486 and the standard deviation is 362. So let's subtract 362, and look what we get. negative 238. So I don't think there's any receivers getting negative 238. I haven't played in the NFL lately. That seems impossible, and it doesn't fit the model well. Why is this? Well, the model here is extremely right skewed. So yeah, really not working, not fitting the model well, just doesn't work. And there we go. Another one. Done. Let's keep working away right here. If you have questions, let me know. Probably go for a little bit more. But jump in with questions if you have them. This is your opportunity. We will be doing a review for the test. But I know this is an asynchronous class, but I want there to be as much help as possible. So you're always free to join in office hours. You're always free to join in these review sessions. I know a lot of times office hours is like 320 students, but you can hop into an office hours and say, hey, Brian, I'm working on this problem. I got no idea how to do it. Just jump in and be like, can you work this problem? And we'll work it. We'll get it done. Let's hear it here. We're working at music. Let's do it. Where is it? Here we go. Another tough problem. Let's get it done. Jump into it. So we got here some data. These are people's ski times going down a hill right here. There were 53 competitors. These are all their times. You watch people go down a hill, and you're like, okay, it took you 114 seconds. Probably me. I'm one of the slower people. And the mean of these observations was 103.02 with a standard deviation, which shows us the spread of the distribution, like how far away things are typically from the mean, of 4.58 seconds. If the normal model is appropriate, what percent of times would you expect to be less than 107? So what we immediately want to do is we want to turn this into a z-score. What is the z-score of 107? They always make these really nice. So we want to do observation minus. Ooh, works again now. If you watched earlier, it didn't work. Over standard deviation. That's the z-score. And basically, I'll tell you this much about the problem, is it always turns out to a whole number. So I'm just rounding decimals, just to make life easier. So it's one standard deviation above the mean. So with it being one standard deviation above the mean, we have to use our normal curve right here. Let's just use it in the general format. So it wants to know, was it above or below? I can't remember. I'm going to take away all the context, and we're just using the z-score right now. So let me disappear. With the z-score right here at one standard deviation, you can see where we fall, and the important thing is going to be the above or below. If it's above, it's 16%. And that's because there's 16% right here. How do I know this? Well, if 68 is inside, 32 is outside, half of 32 is 16. But what would it be if it was below? If it's below, then it's going to be 84. And you can see right here, 84 and 16 add up to 100%. So just kind of make sure you have these values as R and understand how it works, that below this point is 84% of the curve and above is 16. So what does it want, above or below? William's got some good questions. I turned a data frame into a logical by using a less than sign, and I want to use that subset as my data for all correlation functions. Should I change its class or under? Send it to me real quick, William. Maybe we'll take a look at that here in a moment. Yeah, send it to me. Let me take a look. Less than, it wants less than, so it's 84. What is the actual percent of times that are less than 107? So there's 107.6 right here. 1, 2, 3, 4, 5 times are above it. If 5 times are above it, so 5 minus 53, that's 48, of course. 48 times are below it. So that's 90.5, 90.6 when you round it. Do the two percentages agree? No, they're kind of off. It always works that way on this question. They're kind of off. So no, because the normal probability plot shows that the normal model is not appropriate. So if it showed it was appropriate, then it would be good. Data for Q3 is less than... I know it looks like... I know what you're doing. You might want to delete this afterwards. Yep. All correlations, Spearman type interest, Q4. This looks to be... I mean, it is, I can't say if it's accurate or not. But you might want to use, like, remember there's ways to do subset. You then want to take only those observations. I see what you're, I don't want to be too specific. I can't be too specific. but try to make it so that it's a subset. That'd probably be my biggest tip. You can do it that way. Like, I think I know what you're doing, and then delete the code there if you want. Or, like, please delete the code. It's always, yeah. But I see what you're doing, and maybe my only advice, because I can give, like, light advice, is to maybe, but I'm not using the subset I made above for the correlation. Yeah. Because maybe, I think the question is asking you to use only certain things, right? For only certain values, yeah. So I would maybe subset, and you could store that. But that's just going to run a logical check on that vector, right? So you're just pulling that one vector right there, and then you could use that because that's a logical, and then you could use that to subset on that logical. There's definitely a lot of ways to do that right there. Like, that code right there could be used to create subset. Or you could do it with the subset function. So here is the histogram of the data. This can be done in Jump with copy to clipboard. We're just going to copy with Control-C. Awesome work right there, William. Awesome work. Like, great job. This is, like, I want people starting on these things early and seeing this and practicing. So we're just in here in Jump. We're going to paste the data without column names. The reason because it doesn't have a column name. You can actually probably just click the histogram, and there's the answer, which is so cool about the latest Jump. You can see the answer right here. It's got a right skew right to the high towards the 118 area. So it's right skew, and that's the answer. If you want to go more traditional, you'd go here to Analyze Distribution. Let me slow that down. You go here to Analyze Distribution. Great job, William. You're going to click there and double click and go here, and you can see it is right skew. You might say, well, wait a minute, isn't that left skew? Well, the number axis would be reverse. So remember, right to the high, left to the low, wherever the tail goes. What can be seen about the histogram? Choose the correct answer below. It's extremely right skew, so be careful. And don't think that it's left skew there for a moment. Classic, the skiing downhill question. Well, let's head back to space right here. Maybe do one or two more. Let's see. Oh, the steer weights question. I'm sure, William, do you remember the steer weights? This one is with the David M. Lane. I am just coughing and sneezing all today. So with the David M. Lane right here, the highest 10% of steer weights, the lowest 20% of steer weights, the middle 40% of steer weights. Let's go take a look at this. So with this question right here, we're going to use the David M. Lane. The David M. Lane is going to allow us to graph the answers to these questions so we can view it visually here. So usually, like, we could plot these things and look where the highest 10% is, but we can also just literally ask it, where's the highest 10%? Yeah, oh, steer weight's such fun. The big important questions. This is so vet school relevant because vet school is always talking about steer weights. So if we want the highest 10%, it's going to be at a z-score of 1.645. That's where the z-score is always at, or 1.281. Yeah, I talked about the highest 5% by accident. So 1.16, I believe. Yeah. And there it is right there. There's the z-score. So we could actually use this if we wanted. Here's a way to solve the problem that I don't usually do. We should be able to get the right answer if we go right here and times that z-score. So we take the z-score, and then we times it by 86, and then we add that to the mean. And I didn't add it to the mean right there. And by doing this, all we've done right here, and I think I added the right value. No, I did. That's not going to be it. Let me see. I've still got this pasted in. Cool. And then we times that by the standard deviation. And then we add this to the mean. And what have we found? We've just went up on the curve 1.28 standard deviations. Just think about this. You're going here and you're saying I need to go up 1 standard deviation, 2 standard deviations. So you're using the formula. Let's show it right here. Very similar to that formula. Your formula is you're taking the mean plus the z-score times the standard deviation to return the observation. And that's just a reworking of the formula observation minus mean over standard deviation equals z-score. So you're just solving it now for the observation instead of using the formula to get the z-score. And we don't really need to do all this work. We could go right here and plug in the values of 1155 and 86. And there we get the value. And is that close to what I got? Very, very close. Probably within the margin of error it would accept. So 126521. And I think it even has you round to the nearest one decimal. 1265.21. 1265.21. There it is right there. Should take the 3. We'll check the 3 on that. The lowest 20% of steel weights is going to be the exact same thing. We can just go right here and do the lowest 20% by going here to the below. 1082.6. And that's the answer. 1082.6. The middle 40%. And we could do things like the IQR here by doing the middle 50%, but then we can just go to between right here, and there's the middle 40%. So 1109.9. So that's 1109.9, and it goes all the way up to 1200.1. 1200.1. We should have all the right answers. Do we type everything the correct way? We got it. And this one would have rounded up by hand, and it would take it. How much of an error does it have on it? Oh, wow, that's really nice. Let's go crazy here. Yeah, that's way off. I wouldn't expect it to go that extreme, but it's got a little nice plus or minus depending on if you carry all your decimals. And so we do see the by hand calculation we did right here using the z-score would work. And so if you think the 20th percentile has a z-score of, is that one not 1.2818? No, that's not going to be, that's 0.842. The z-score for that one is 0.842 for the 20th for the my brain's breaking. Is that the 60s percent? The lowest 20, actually I don't know what the z-score for that is. So the lowest 20%, I do not know the z-score for that one off the top of my head. So the lowest 20% in terms of z-score has a z-score, oh, it is 0.842. I see things I know that I don't know. 0.842, it's just one of the ones we use on the assignment. 0.842 is the z-score. So what does that mean? We would need to take the mean and go down to that many standard deviations. So remember, we would just take our mean right here. Let's look what the mean of the question is. So the mean of the question is 11. Yep. So we take mean plus negative and then 85. And that's going to equal the observation. So I think it was at 85. I think I just messed that one up. 86. There we go. And let's take a look right here. 86 times 0.842. That's how far we are below the mean. And then we're going to take this value right here and subtract it from this. And this is just doing it by hand, which is important to know for the test. 1082.6. And that should be, yep, 1082.6. And that's what we get doing it by hand, showing that we don't exactly need the applet if something on the test were to give us the z-score. But really good practice right here on these problems, just using the values and more steer weight stuff. So very similar. This is using the percentile stuff we just did right here, so we can see the exact same sort of questions. Using the percentiles, and I think we should be able to, so let's take a look right here. Really? Why is it going to look like that? Look at this. Beautiful. So we need to put in the mean and the standard deviation. The mean is this right here. The standard deviation is 95. And now we want the 58th percentile. Now, an important thing to know about percentiles is they start at the bottom. Like, you wouldn't want to be in the lowest percentile on the test. Your test grade would be very low. But as your percentile goes up, so does your test grade till you get to like the 50th percentile, which is right here at the center of the distribution. Very high percentiles like the 90th percentile are going to be here towards the top, but the 58th percentile is going to be towards the center, and we have the answer right there of 1146.18. The steer weight representing the 93rd percentile, so that's just going to be over here on the curve. Make sure we're doing the below, is 1267.2. And then the IQRs, where usually people get stumped on this one, but that's the middle 50%. So if you notice, we have here the first quartile, which we could confirm this by going here and putting in 25%. That is the first quartile, and this is the third quartile. So this is showing us the IQR here, but we get both numbers conveniently by using either of the two bottom buttons, the middle 50% or the outer, but that's just kind of flip-flopping the way we're viewing it. Either or is fine. So now that we have both these numbers, remember the IQR is just a distance. When we talk about the IQR, we're just asking, well, how far away is Q1 from Q3, the range of the middle quartiles? And so now we're just going to take the values right here to find the range of them and take big number minus small number. In truth, it doesn't matter which way you subtract them because it's always a positive difference. It just makes more sense to subtract them so you get a positive difference, like max minus min. This isn't the max, but it's the big number, Q3 minus Q1. So you get a positive difference right here, and that is the IQR. Round to the nearest whole number, 128. Don't mind if I do. And get another 100. Good stuff right here. That's got the steer weight problems. Some really good tricky stuff. We'll hop back here to space. Let's do this. What questions are there? Remember, always feel free to swing by. Ask the questions. Ask those questions. Let me know where you're stuck. Chapter 5 is a tricky one. IQs, that one's pretty easy with the information we gave. We've covered a good set of questions right here. Different types of questions. You know what? We could do this one right here to end it. Let's hear it here. Subset. So I can't say if you're right or wrong. So here's what I would do, William. Here's what I would do. I would... Remember, delete it afterwards. Delete it afterwards. I can't say if you're right or wrong. So I can't say that about the take-home at all. But I would look at the result and be like... So you can always view what you make. Remember to view what you make. And I would look at it and be like... Does this make sense? Like, when you look at it... And then you're like, okay, did it do what I wanted it to do? Does that make sense, William? And so I can't say if you're right or wrong. I can't find Q3 or Q1. Maybe. So here's a hint I can give. You don't have to use the select argument. If you don't use, so you can use select if you want to select certain things. Also, column names are characters. So here's the most hints I can give. In all correlations, you should be able to. Remember, column names are characters. So I can't say quite what to do, but just remember column names are characters. That small things I can say. I can't say if you're right or wrong. I can just say column names are characters. That's which to someone who has no idea what we're doing. That does it make sense what I'm saying with like column names are characters? So they should be referred to in the way we refer to characters. Does that make sense, William? Like if I say column names are characters. And then take a look at what you create. Maybe you're catching what I'm saying. Can't say if you're right or wrong. Column names are characters. See, as we learn this here, and William, you hadn't coded before this, had you? Because you picked up on that. Maybe you did. I'm not saying you did or didn't. But this is the goal, is that I could communicate things like that to you pretty quickly by just saying, column names are characters. Yes. And William, I'm just really proud of you. I just want to say that, and I'm proud of everybody. But it just takes practice. It takes time. Some people who... I just repeat the story time and time again of my student who after they took 320 and 474 in the summer, and by the end of the summer, they were beating out people who've been coding for a year. So let that be you. Let that be, it's just like someone who goes to a basketball camp. Oh, shucks. Who do you think would be better? Someone who goes to a basketball camp where Michael Jordan and LeBron James are their coaches versus someone who says, I'm just going to learn how to play basketball on my own by watching YouTube videos. Who's going to be better at basketball? Person who goes to the basketball camp with LeBron James and Michael Jordan. You signed up for 474? Yes. For this summer? Oh, man. It's going to be crazy. I'll tell you. I'm making 475 right now. I'm doing a lot of stuff in the background. Woo! This is one of my busiest summers ever. So it's pretty busy. But I'm here for you guys. So I wish I was the Michael Jordan. I wish I'm the who am I? I'm the, what's his name? Can't think of his name now. He's my favorite basketball player. He's the guy with the hair color. He always changes his hair color. Probably my favorite basketball player of all times. I'd love to meet him. He's crazy, though. Muggsy Bogues. Muggsy Bogues is pretty cool. He was on Charlotte Hornets. Muggsy Bogues. I don't know much about Muggsy Bogues, but he seems like pretty chill. The guy I like, he's really crazy. Yeah, Dennis Rodman. Yeah, yeah. I'd be a little afraid to meet him because he's a little... he's Dennis Rodman. I mean, I'd... Like, if I met Dennis Rodman... If I met LeBron James or someone, and he was like, hey, Brian, good to meet you. I'd be like, oh, dude, LeBron James. Dude, you're awesome. If I met Dennis Rodman, he was like, Brian, good to meet you. I'd be like, I don't know where you've been. He's Dennis Rodman. dude is interesting. I mean, I just think he's fun. Toss me some points. Of course, of course. Is it like The Witcher right here? Is that what we got going on right here? Some Witcher references maybe. But like if I met LeBron James, that'd be awesome. Like if he was like, "What's up, Brian?" I'd be like, "Hey, what's up, LeBron?" I'd be like, "Seriously?" I'd be like, "You dude, you're LeBron." But if I met Dennis Rodman, yeah, I think people get the point. It's just Dennis Rodman is so interesting, and he was so here's why I really like Dennis Rodman is I'm not a big fan of basketball. I know enough about basketball, but I'm not a big fan. You're leaving now. You're welcome. Anyone who's watching this afterwards. Growing up, my brother watched basketball all the time, and basketball it's good sport, it's good stuff. But I don't like sports usually. I don't want to watch baseball. I don't want to watch football. I don't want to watch hockey. Not a big fan of basketball. Just there's no sport I really just want to watch on TV. But when Dennis Rodman was playing, I'd actually care to watch. I'd be like, this is interesting now. And he was just so much fun. It's like what's his name? The two guys who played on the Celtics together, they were a lot of fun to watch. So yeah, I mean, I want to watch sports when sports are interesting. They don't need to be nothing crazy, but Dennis Rodman was a lot more fun than just watching basketball because I don't care. It's not a sport it's not my thing. The Brian, aren't you wearing a football shirt? No, I'm wearing Vol for Life right here. VFL, Vol for Life. That's what I am right here. But with that, so feel free if you want in the comment section of the video. No one's watching this right now, probably. Put your favorite sports person. Like Sergio Garcia, I thought made golf more interesting in the early 2000s. And Tiger's excellent. Tiger's awesome. Tiger was good to watch just because he was crushing it, because he was like just destroying all the records and doing amazing. But then Sergio Garcia was a lot of fun to watch because he would just like he'd hit like an amazing shot and he'd be like, yeah, like jumping up, like running, or he'd hit like a really bad shot and he'd be like, and you're like, dude, this is a little more fun to see how he's gonna react to each shot. Than just like, okay, we're on a par 4 and swing back. Okay, good shot. Down the fairway. Good thing. Clap, 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 clap. Yeah, it's boring. He hits it and he slices the ball and he's like, just like tosses his club, and then they're like, Sergio Garcia is being warned for throwing his clubs. Why is the take home easier than assignment 5? There you go, because it's just answers to questions. I like hearing that right there. I don't know, because you've been practicing, because you're doing well on the assignments, and you know why? William, I got the answer for you right here. It's easier, and we'll put on our ending music right here. It's easier because all the questions you've been doing, you know how to do because you've been doing all the assignments. So basically 2/3 of it right now is just review. And you're like, well, I just did this yesterday. I just did this a few days ago. So every time you're seeing a question, you're like, well, I have a homework assignment that covers this. I can just look at the code right here and it says do this. Okay, subset this, do all correlations of this, find the spearmint of this. So I would hope the take home would be easier because it's meant to be like review of what you've been doing. So if you did the previous assignments, some people are going to find the take home to be impossible because they're like, whoa, this covers a whole heap of things. Well, all correlations, what chapter is that in? When did we do mosaic plots? When did we do box plots? When did we do these? So you got nice job right there. Little bits. And if you get stuck, just put it up and then go look at the notes and review and be like, okay, I need to subset this and make this work. Well, I think that's got it. With that, everybody, we'll be back here tomorrow. Mubot, where are you at, Mubot? You're going to be in front of me, aren't you? Mubot?
I am Mubot.
Bye for now, everybody. Bye, Mubot.
I am Mubot.
Shut up, Mubot. You good man. I'll see everybody later. Bye.
Yeah, 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 yeah.